Students, let us revise what we have done so far. So we were starting this chapter number 2, electric potential and capacitance, and we were trying to find out the work done by electric force in moving a charge from one point to another. So what we are doing is we are trying to find out work done by electric force. So we all know that work is force into displacement, and work is a scalar quantity. In vector form, it is given by the dot product of force and displacement F dot S. You can also write it as Fs cos theta, where theta is angle between force and displacement. You can see this diagram where we have a positive charge and there is another test positive charge small q, which is being moved from A to B. So you can see the displacement is in the direction from A to B. Now this charge q will experience a force because of this positive charge capital Q in this direction. So you can see these two things, force and displacement, they are in opposite direction. So the angle between force and displacement is 180 degree. So by definition we all know that work done is force into displacement F ds cos theta, and when we put the value of theta, we will get that work done come out to be minus k capital Q small q by r square. So if we integrate it from these two limits from r1 to r2, you all know what we will get. So we have this expression of work done minus k capital Q small q by r square dr. So by using this formula of integration x raised to power n dx is equal to x n plus 1 by n plus 1, we will get this expression that work done come out to be k capital Q small q 1 by r from r1 to r2. What we will do is we will put the upper limit and lower limit. First we will put upper limit, then we will subtract it from the lower limit. So we got the work done k capital Q small q 1 by r2 minus 1 by r1. So this was the expression of work done. Now we were trying to understand what is electric potential. Electric potential is always defined at certain point. So at any point, electric potential is defined as work done by the electrostatic force in moving a unit charge from infinity to that point. So R1 will be infinity and R2 will be R. Remember, R1 will be infinity and R2 will be R. So here in place of R1 we will put infinity, in place of R2 we will put R. Right? Remember that R1 is infinity and R2 is R. So we are going to write this expression again. So by definition, electric potential is defined as work done per unit charge, or you can say because you are moving this unit positive charge from infinity to the point where you want to find out the potential. So value of q is 1. So you can simply divide q by q. Q will be cancelled out, and I told you in place of r2 we are going to put r, and in place of r1 we are going to put infinity. So 1 by infinity will give you 0, and potential will come out to be k capital Q by r. So we have done till this topic. Now I want to tell you that this electric potential is a scalar quantity, and for positive charge the potential will be positive, and for negative charge the potential will be negative. So suppose if I have a positive charge capital Q and I want to find out potential at this point A, which is at a distance of r, then at this point potential at A will be k capital Q by r. If you want to find out, if someone asks you find the potential at point B, which is say at a distance of r1, then at point B the potential will be kq divided by r1. So because of positive charge the potential is always positive, and because of negative charge, what will be the potential? Say we have a negative charge minus q, and because of this negative charge I want to find out the potential at say this point x, which is at a distance r2. Now potential at x will be minus kq divided by r2. So what we have learned is that potential is a scalar quantity and it is added like number, and because of positive charge the potential is positive, because of negative charge the potential will be negative. Let us consider a case where we have a system of charge. We have this positive charge q and we have this negative charge q. What do you think? What do we call such a system? The system is actually an electric dipole. And if someone asks you find the electric field at point in between, you'll see that because of positive charge the electric field is in this direction, because of negative charge the electric field is in this direction. So these two electric field will add up to give you total electric field, which is 2 times E. But unlike electric field, if I ask you find the electric potential at this point, which is just in the middle of these two charges, two equal and opposite charges, you'll see that because of this positive charge the potential will be, say the distance is A, and here the distance is also A. Because of positive charge the potential will be kq by A, and because of this negative charge the potential will be minus kqq by A. So what is net potential? I told you that potential is a scalar quantity, you can add them like numbers. So total potential will be V plus Q plus V minus Q, and you'll get 0. So if someone asks you can you make a system where electric field is non-zero but potential is 0, this is the system where electric field at point P is 0, electric field at point P is non-zero but potential is 0. Now there is a question for you, can you devise a system where we have electric field 0 at that point but electric potential is non-zero? So that is the exercise for today. I hope you'll do that. If there is any doubt, you can always ask.